Okay, we're going to talk about neural networks, and I'm taking this from a very good book which I recommend called Discovering Knowledge and Data by Daniel LaRose, and I'm going to be looking at that. So, neural networks, the inspiration for neural network was from learning about animal brains and interconnected sets of neurons. And we use what's called artificial neural networks in data mining. And this is a picture up on top of, uh, I guess, a neuron. It has dendrites, the cell body, an axon, like this. And then this is the model of that using an artificial neural artificial neuron model. And basically, as we've said already, you have a bunch of inputs and you feed it in, and then you try to get an output. You try to predict an output. So you can see here that we're putting in x1, x2, xn, and we're getting out some kind of y. And what happens in between is the whole point. So it says the inputs x sub I are collected from upstream neurons. So sometimes you'll have like a whole bunch of what are called nodes. Anyway, you can ignore that for now. And combined through a combination function such as a summation, and then input into an activation function. So you get stuff here, and then you put it into another function. Just basically, this is the sort of brains of the neural network. So whatever you do in order to get an intelligent response, and uh, produce an output response Y, which is then channeled down. Then you may have, this may be sort of repeated, but we'll ignore that. What types of problems are appropriate for neural networks? Um, One of the advantages of neural networks is that they are quite robust with respect to noisy data. So that means that if you have noisy data, you can still use a neural network and it seems to work well. Because the network contains many nodes, um, we'll see what that means. With weights assigned to each connection, we'll see what that means. The network can learn to work around these uninformative or even erroneous examples in the data. So noise means that you have data that's messy. Um, so in other words, bad data in the set, sort of bad data. However, unlike decision trees, which produce intuitive rules that are understandable to non-specialist, neural networks are relatively opaque to human interpretation, as we shall see. So uh, when we talk about decision trees are kind of, you can sort of understand the logic that's happening in them, but in a neural network, basically, you don't see what's happening inside. You just get the result. You just get the output. Okay, first issue is input and output encoding. Uh, so one possible drawback of neural networks is that all the attribute values must be encoded in a standardized manner. So what that means is like if you're inputting a lot of different kinds of variables into the neural network, for example, one is income and the other is a person's height. Suppose those are two variables that you're inputting, income and height. The income is huge, right, compared to height. Height might be like, what, 175 centimeters, for example, and income might be, if you're talking about, for example, Japanese yen, might be like um, 4 million or 5 million or 6 million or whatever. So the scales are very different. You don't want to do that with a neural network, so you have to sort of scale everything. So taking values between 0 and 1. Really, you want everything to be between 0 and 1. Now some, like Weka, you don't really have to do that because it does it for you, but if it didn't do it for you, you'd have to do it yourself. Um, even for categorical variables. So even categorical variables have to be between 0 and 1, whatever that means. Later, when we examine the details of the backpropagation algorithm, we shall understand why this is necessary. For now, however, how does one go about standardizing all the attribute values? For continuous variables, this is not a problem. Remember, so for continuous or real valued or numeric value variables, it's not a problem. We can apply what's called the min-max normalization. So what is that? So if you want to convert x to a standardized or normalized value, so let's take say height, which maybe you have somebody who's 175 centimeters, so x is 175. And then you take the minimum value of x. So suppose that you have a bunch of people and they range in height from 150 to 200. So the minimum value would be 150. So you take 175 minus 150, right? So what's that give you? That gives you 25. Divided by the range for this height variable. So the range we said was 150 to 200 means the range is 50. So divided by 50. So what do you get? You get 25 over 50. You get 1/2. So you would say that someone whose height is 175, their normalized height is 1/2. Okay? This works well as long as the minimum and maximum values are known and all potential new data are bounded between them. Neural networks are somewhat robust to minor violations of these boundaries. If more serious violation, okay. Categorical variables are more problematic, as might be expected. If the number of possible categories is not too large, one may use indicator or flag variables. For example, many data sets contain a gender attribute. So if you're inputting data and part of the data set is a person's gender, so one of the variables is gender, so you have male or female as the possible values for the gender attribute or unknown. Since the neural network could not handle these attribute values in their present form, we could instead create indicator variables for female and male. Each record would contain values for each of these two indicator variables. Records for females would have a value of 1 for female and 0 for male, while records for males would have a value of 0 for female. So in other words, you'd create two new variables, one called male and one called female. And if if the record was a male, then the male variable would be set to 1 and the female variable would be set to 0. Records for persons of unknown gender you could set for 0 and 0. In general, categorical variables with k classes may be translated into k-1 indicator variables, as long as the definition of the indicators is clearly defined. So in other words, in this case, they said records for, in general, categorical variables with k classes. So this is a categorical variable gender. And how many classes are there? Male, female, and unknown. So there are 3 classes. How many variables did we need to encode that? We created 2 new variables, one male and one female. And with that, we could encode all possible cases, right? We could encode male, female, and unknown. And so if you have k classes, you need k-1. We had 3 classes, we needed 3-1, 2 indicator variables. Be wary of recoding unordered categorical variables into a single variable with a range between 0 and 1. For example, suppose that the data set contained information on marital status attribute. Suppose that we code the attribute values divorced, married, separated, single, widowed, and unknown like that. And so we might be tempted to take marital status, which can take these values, can take the values divorced, married, separated, single, and widowed and unknown. So we have a single variable called marital status, and then for some people the marital status will be married, for some other person the marital status will be single, and so on. So we might want to recode these because we see that we have to recode to numbers. In fact, we have to recode to numbers between 0 and 1. So we might want to recode these, and we might say, okay, let's say divorced is 0, married is 0.2, separated is 0.4, single is 0.6, and so on. So they say, be careful, don't do this actually, because this coding implies, for example, divorced is closer to married than is separated, and so on. But that's not what we meant when we did this encoding. The neural network would be aware only of the numerical values in the marital status field, not of their pre-encoded meanings. So it's only going to would thus be naive of their true meaning. Spurious and meaningless findings may result. So how would you handle marital status instead of doing it that way? We know that it has to be between 0 and 1. How would we handle it? Well, we'd handle it just the way we did gender. So in this case, marital status can take on how many different values? Divorced through unknown. So how many? 1, 2, 3, 4, 5, 6. So we need how many indicator variables? We'd need 5. So you might have one indicator variable called divorced. So you create a new variable. Throw out marital status. Throw it away. Don't use it. Instead, create a new variable called divorced, and it's going to be a 0, 1 variable. Create another new variable called married, and it's going to be a 0, 1 variable, and so on. So create 5 new variables, all 0, 1, and then you can cover all 6 cases. Okay. With respect to output, we shall see that the neural network output nodes always return a continuous value between 0 and 1 as output. How can we use such continuous output for classification? So remember that classification as opposed to estimation. So estimation means that the output is numeric. Classification means that the output is categorical. So you might want to classify somebody as owning a car or not owning a car. So that's classification, right? Either they own it or they don't. Either yes or no. Not, for example, income. Income would not be classification. Income is prediction. I'm sorry, is estimation. But they're saying that neural networks give us continuous output. So how can we use that for classification? Many classification problems have a dichotomous result. So in other words, just yes or no, or 0 or 1. An up or down decision with only 2 possible outcomes. For example, is this customer about to leave our company's service or not? So you might want to build a neural network to make predictions about whether a customer is going to leave your service or not. For dichotomous classification problems, one option is to use a single output node, such as in figure 7.2, with a threshold value set a priori, which would separate the classes such as leave or stay. So let's look at that. Where is that? Here. Is that it? 7.2? Yeah. So I think that's right. Yeah. With a threshold value set a priori, which would separate the classes such as leave or stay. For example, threshold of leave if the output is greater than this. Remember, the output is going to be a number, so if the number is greater than 0.67, we'll classify that person as we expect them to leave, and if it's less than 0.67, we would classify them as not leaving our service. Single output nodes may also be used when classes are clearly ordered. For example, suppose that we would like to classify elementary school reading prowess based on a certain set of student attributes. So we want to, the output is how well somebody reads. And based on a certain set of student attributes, a certain set of inputs about the student, then we may be able to find the thresholds as follows. If the output is between 0 and 2.5, classify them as first grade reading. If it's between here and here, classify them as. So we can use this scheme also for classification. This time when we have 4 possible values for the output. Fine-tuning of the thresholds may be required, tempered by experience and judgment of domain experts. Not all classification problems, however, are soluble using a single output node. For instance, suppose that we have several unordered categories in our target variable, as for example with the marital status variable above. So remember, marital status, we had several categories and they weren't ordered. In this case here, they are ordered. We have 4 outputs, but they're ordered, right? First grade is less than second grade, is less than third grade, is less than fourth grade. However, when we talk about marital status, we don't have that kind of order. This is less than that, is less than that, is less than that. For example, if marital status was our target variable, the network would have 6, or let's see, sorry. In this case, we would choose to opt a 1 of n output encoding, where one output node is used for each possible category of the target variable. For example, if marital status was our target variable, so the output variable, we could have on the output node, we didn't really talk about what's meant by the node, but the output node would have we would have 6 output nodes in the output layer. We haven't talked about this yet, but for each of the 6 classes, divorced, married, separated, single, widowed, and unknown, the output node with the highest value is then chosen as the classification for that particular record. This is kind of jumping ahead of ourselves to talk about this, I guess, but one benefit of using 1 of n output encoding is that it provides a measure of the confidence in the classification, right? Because if you assign a value to each possible class, so you assign a value to divorced, married, separated, single, widowed, and unknown, then suppose divorce is 0.7, married is 0.3. You can sort of treat these as probabilities, and then if divorce is the highest probability, we'll say, okay, we expect this person to be divorced. Remember, here we're talking about marital status in this case as being an output variable. We're trying to predict it, not as part of our input. Okay? So they're saying that you kind of get, when you do it this way, you kind of get, when you assign these numbers to these outputs, you can sort of treat these numbers as probabilities. So they give you a measure of confidence in the classification. So if this one is zero point 0.7 and this one is 0.05, 0.05, 0.05, 0.05, 0.05, then we're pretty confident about this one because it's so much greater than the others. Classifications with low confidence, small difference in node output values can be flagged for further classification. So if it wasn't 0.7, but it was really close to the other ones, then we might sort of do something else to it later. Okay, let's stop here and continue next time with neural networks for estimation and prediction.